All right, so our first puzzle or riddle that's going to play off of our discussion of hashing algorithms and general crypto systems is going to be this cute little question of trying to find the parent of a child. So it's a really weird way to frame this question, but it does work very nicely. So anytime we have these processes that have different generations, we typically run them in the forward direction. The idea is that I give you the initial configuration of Glider Man, and then you click, what's the next generation? What's the generation after that? What's the generation after that? And you run this process in the forward direction. And then at the end of the day, you end up with whatever configuration you have. And you're like, cool, that's just what happens after 20 generations. What we want to do now is we want to start working in reverse. Basically, we think about having that 20 generational structure, having a bottoming out point. We're going to have some ultimate little kid at the very bottom, and we're going to ask, who was their parent? And if that works, we can ask, who was their parent? And then we can ask, who was their parent? And if possible, can we run this thing all the way up the tree to actually identify who the initial, great, 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 great grandparent happened to be? What we're going to see along the way is that there's not going to just be a unique parent. Certain configurations actually have no parents. So there's going to be this notion of some orphans, is that we can't work in reverse. And there's just a multitude of pretty cool things that are going to exist here, which hopefully in the back of your brain is starting to make the connections that this is exactly how some of these hashing algorithms work. Basically, we mix and scramble and mix and scramble, and we go down this hole. And the hope is that we can't try to click our way back out. You can try to maybe go backwards one click, but then that's going to open up this kind of a web of all of these possibilities. And the hope is that that web just becomes far too chaotic that you can't go back those, 18 or 24 different passes, is that it just becomes way too chaotic to have any chance of going in reverse. Same type of thing is going to happen in this game as well. So I alluded to it a little bit before. There's this notion of undecidability, is that we have this struggle, and you're going to see it very quickly emerge, is that it's going to be very chaotic almost immediately. Even for some of these tiny little processes where I have this little number 7, just going in reverse one step is going to bring out a bunch of different parents, so that if I had to go in reverse again and again and again, then I'm just going to have this tree of possibilities, and it's going to become just completely unruly. But it is pretty fun to look into. It has a nicer feel rather than just XORing a bazillion things. I mean, like, good luck trying to claw your way out of that. At least this has this kind of nice image of like, well, what happens if I do this? And what happens if I do this? And what happens if I do this? So it's a fun way to seal some of these things together. So that's our goal. So here's my child. I'm going to call it C. My goal is to try to identify some parent, which I'm going to call a P. And the hope is that if I take this P and shove it through this next gen algorithm, that it's going to kick out the child. To help us out, we're actually going to make use of some of that binary structure that we had in the hashing algorithm world. And you can kind of already see it when you start looking at this and kind of storing this as this big 2-dimensional array. So this little child C is currently drawn in this little 4x4 grid, which is hopefully screaming at you as that little thing essentially is going to look like some 16-bit number, which is exactly how I want to store this. So the idea is that that top row is going to be a top row of 4 zeros. Then the second row is going to be 0, 1, 1, 0, which is that. And then it's going to be 0, 0, 1, 0, which is that. And then it's going to be 0, 0, 1, 0, which is that. So I have these 4 little blocks of 4-bit numbers. Well, I can just glue all of those together to end up with this nice 16-bit number, which is what it is. And then if I want to convert this thing back into decimal format, I can easily do that. And you can see that this child I can view as a C, or I can view it as the number 1570. In total, you can start to see how many possible parents there are going to be. Well, any parent could be basically any 16-bit number. So we're going to have 2 to the 16th number of those, which is like 65,000 or something. Should definitely know what 2 to the 16th is a little bit better. So 65,536 if I use my cheat sheet. So the goal here is that we're going to blast through all possible parents and then play this game of, is this your kid? Is this your kid? Is this your kid? So it's got this, I don't know, terrible like amusement park ideas that I found this child, and I'm going to go ask, 65,000 different parents of like, is this your kid? Is this your kid? Is this your kid? Is this your kid? It'll then open the idea up to that there might be multiple parents, which is totally going to happen here. But it also then begins poking into this question of, are there some states that can never be achieved? Are there some quote unquote orphans? So some kids that don't have parents. And there actually are. So in Conway's Game of Life, there are some configurations that can never be achieved. There's no other things that are actually going to funnel into that thing. So on D2L, I'll give you a couple links for some of them. They're a little bit larger than some of these, and I don't want to brute force all of the possible parents to show that it doesn't actually work, because I don't have the computational power right now to do that, and you don't want to sit and watch that thing spin over and over and over. So we'll easily go through the 65,000 versions of parents for this example, and we'll see a couple of other examples in your activities and things like that, where you can kind of blast through different things to see different parent structures emerge, and it's just kind of fun all around. All right, so in this one, we actually do have a variety of different parents. So here I've drawn the child, so the thing that lives at Gen 1. So this number 1570, drawn in binary, but stacked afterwards. So the smallest quote unquote number that would actually exist as the parent is this one. So 8289. And you can see that that blue configuration would in fact generate that child. And you can go back and check. So basically this cell right here would become born because it has 3 neighbors. This cell right here would become born because it has 3 neighbors. This one would be stable because it has 2 other neighbors. And then the little tail on the 7, the top right, the top left thing, would then be born because it also has 3 neighbors. And the other things that were currently alive, those would all die off. And they would all die off due to loneliness because they all only have 1 neighbor. So that thing is definitely a parent of this thing. So is the purple one. So you can see that this one would generate a birth because there are 3 neighbors. That one's going to be born because there are 3 neighbors. This one's going to be born because there are 3 neighbors. And this one will maintain because there are 2 neighbors. And everything else would die off because there's only 1 neighbor. So they die off due to loneliness. I really like the one on the way right because it has everything dying, and then the way that we create the little 7 is purely through the birth process. So born, 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 and born, and then everything else is going to die. So it nicely constructs this little 7. So there's this idea like you're using this white space and then it like all sucks into it afterwards. So this one does in fact have some parents. In fact, it's got a variety of parents. So I'm just going to quickly jump into the implementation of that so you can see what it looks like. Hopefully I can swap it over and everything is still up and running. So the same stuff that we had before. So the next gen algorithm up on top. Here I'm going to feed in this little child of 7. I've given it the ring of zeros around it, so I have that buffer, so everything above is going to work nicely. So really be thinking about that 4x4 block is going to be living inside of that 6x6 block. So there's my cool little 7. Here's my number 1570, which is how I'm going to view that thing. And that's the little bit that I have down below, is that if I take that number 1570, convert it to binary, append a few extra zeros, or insert, I should say, a few extra zeros into the beginning to make the length of that 16. And then I'm going to create those 4 little blocks of 4. I can then take any number I'd ever want and convert it into this cute little configuration. In particular, I can take the number 1570 and I can regenerate this little 7 out of that. What that does for me is that it gives me a really cheesy way to blast through all possible parents doing this game of, are you my parent? Are you the parent? Are you the parent? Are you the parent? Are you the parent? And the way that I'm going to do that is I'm just going to have a little loop that's going to run through all of the possible n values, starting at 0, which would be the blanked out graph, going all the way up to 2 to the 16th minus 1. So it's going to have all 16-bit numbers. And then I'm going to blast through all of them. And you're going to see if the parent is in fact the parent of that child. So if child is equal to the next gen of that parent, so I've gone to the parent and I've asked, is this your child? And they would say yes. So child matches up with that current C. Then I'm going to append that number to the list of parents. And then I'm also going to print out what that number happens to be, as well as its binary equivalent. Printing out the binary one just because I was curious about which one had a whole bunch of 1s and which one has a whole bunch of 0s to try to get some cute examples, which is where that extra example of 8401 came from. I was looking into some of those. So there's what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18-ish or so parents that are going to exist here. Technically, there's going to be an infinite number of parents because if you were to have this on a really big structure, you could always put just little singletons way far away. these little singletons are going to automatically die due to loneliness. So you actually have an infinite number of parents. So once you find one, you will always have an infinite number of parents. These ones then become some of the more interesting ones because they're having different structures close to the actual child, whereas dotting in extra little singletons way out in the outskirts isn't really that interesting. It's just kind of like unnecessary white noise that exists out there. And then this is the process of just blasting through a couple of them. So this first one is going to be the smallest number. So that was the 8289. So that was the smallest n that kicked it out. And then I printed out the biggest one. So I have things that are going to exist up in that top left. And then this was the one that had just kind of a cute random structure where I had like that ghosted out 7 in the middle, that everything emerged via births. And then if you want to, you can click that random process over and over and over again, and you can see different things emerge on the back end, which is a lot of fun. I don't know. I'm weirdly entertained by them. I can watch Game of Life things go for hours and hours and hours, and trying to identify these parents are also a super cute thing that I can do for hours and hours and hours, because I'll try to do them by hand, being like, well, what happens if I do this and this and this and this? And then it's just like, oh, this is just a terrible riddle. And now I just want to brute force this thing and see what's going to emerge. But then I'm like, well, what happens if it's really big? Then I can't brute force this thing and I got to do things more elegantly. And then it just snowballs out of control. And then an hour later, I've just like driven myself mad trying to draw all of these little structures. And I was like, okay, I probably should do something else, but I really just want to play with these. So hopefully you can get extra excited about it and just blast through a whole bunch of different parents as well and see why some of them are actually parents and why some of them are not. So like what would happen if you added one extra little square? There's kind of this delicate birth-death process. And if you change just minute things, the whole game changes. So it's pretty fun to play with. I'll let you see some of them on your activity. We've got some more goods to look into.